All right, tomorrow's the big day, the AS Chemistry multiple choice paper. So in this explainer, we're going to break down our final data-driven predictions for the 9701/12/FM/M26 paper, all to help you really focus that last-minute revision.
First things first, we need to get inside the examiner's head. It's not just about what you know, it's about how they're going to test it. So let's dive into some of those common pitfalls that can trip up even the most confident students and cost you valuable marks. To do this, we've really gone deep. We've dug through old papers, sifted through examiner reports, and looked at the new syllabus to pinpoint those high-probability topics and the really tricky concepts you absolutely have to nail down before you walk into that exam hall. Okay, a quick but really important disclaimer here. Think of this forecast as a high-impact revision guide. It is absolutely not a substitute for proper comprehensive study. Use this to sharpen your skills on the stuff that's most likely to come up. But just remember, at the end of the day, Cambridge has the final say on what's actually in the paper. Right, let's get into it. We're starting with the specific concepts where examiners just love to set traps, to separate the top students. These are the questions that can really make the difference between getting that A or a B. You are almost guaranteed, you can practically bet on seeing a question about Boltzmann distributions. Understanding not just what the curve is, but how it behaves, that's absolutely crucial. And remember, that whole area underneath the curve, that's just the total number of molecules you got in your sample. And these shifts, this is what examiners love to test. So let's look at that first point. If you decrease the temperature, the peak shifts to the left, to a lower energy, and it gets taller. Why? Because the total number of molecules hasn't changed. Now, for the second point, what if you add more gas but keep the temperature the same? Well, the peak's position doesn't move, but it gets higher because you've literally increased the total area under the curve. Okay, next up is the ideal gas law. And let me tell you, every single year, without fail, students who know this equation perfectly still manage to lose marks. And you know why? Simple, painful unit conversions. The point here is so crucial. You have to convert everything to the standard SI units before you even touch your calculator. Pressure has to be in pascals, temperature must be in Kelvin, and here's the big one, the trap they always set. Volume has to be in cubic meters. They love giving it to you in centimeters cubed, so just burn this into your brain. Multiply by 10 to the minus 6 to convert. Don't let them catch you with this one. This visual here perfectly illustrates a key trend in periodicity that they love to ask about. What happens when you react period 3 chlorides with water? On the left, you've got good old sodium chloride. It's got that giant ionic structure, so it just dissolves, giving you a perfectly neutral pH 7 solution. But look at the right. The simple covalent chlorides like silicon tetrachloride or phosphorus pentachloride, they react, let's just say, vigorously. It's a hydrolysis reaction, and you get these steamy white fumes of hydrogen chloride gas and a very acidic solution, somewhere around pH 1 or 2. Here's a real classic from Group 2 chemistry, thermal decomposition. If you heat 1 mole of a carbonate, you get just 1 mole of CO2 gas. Simple. But if you heat 1 mole of a nitrate, well, you get 2 moles of that toxic brown NO2 gas plus half a mole of oxygen. That's a grand total of 2.5 moles of gas. This is such a common trick question, asking which reaction makes the most gas. Now you know. All right, let's move into organic chemistry and talk about isomerism. It is very likely you'll be asked to count the chiral centers in some big, complicated molecule. The rule is actually pretty simple. You're just looking for a carbon atom that's bonded to 4 completely different groups. And remember, this only applies to singly bonded sp3 carbons. Just totally ignore any carbons that are part of a double bond. Okay, this is a huge data interpretation skill from the new syllabus. In mass spectrometry, if you see 2 peaks way over on the right of the spectrum, the M and M+2 peaks, their height ratio tells you exactly which halogen you have. It's like a secret code. If you see 2 isotopes of chlorine, you'll get a 3:1 height ratio. If it's bromine, its 2 isotopes have almost the same abundance, so you get a perfect 1-to-1 ratio. Memorize these ratios. Seriously, it's a gift from a mark. So let's see how this all comes together. We put all of this into our data-driven probability scorecard for your paper. We've basically compiled the topics that have the highest chance of showing up based on the syllabus weighting and how often they've appeared in the past. So here it is. This is your high-yield revision list for these last few hours. We are 95% confident you're going to see a question about finding an element's group from the big jump in its ionization energies. A Hess's law calculation is almost a dead cert.
You'll also probably need to explain how a catalyst affects a Boltzmann curve. For inorganic, definitely review the solubility trend of group 2 hydroxides. Remember, it increases as you go down the group. And for organic, make sure you know the iodoform test and you're comfortable counting up sp3 versus sp2 orbitals.
Knowledge is one thing, but being able to execute under pressure is something else entirely. So now I'm going to give you a simple strategy to help you avoid those silly little mistakes that can happen when that clock is ticking down.
Okay, here are 3 really practical steps. First, as a final check when you're done, count your answers. Cambridge actually designs these papers to have a pretty even mix of A, B, C, and D. If you look down and you've got 15 A's, go back and check your work. You've probably fallen for a distractor somewhere. Second, get involved with the paper. Underline keywords, circle the numbers in a calculation. It really helps keep you focused. And third, for any complex question, just draw it out. A quick sketch of a Hess cycle or an organic mechanism can suddenly make the answer totally obvious.
So, we have covered the traps, the most likely topics, and a strategy for the exam itself. What's the single most important thing you can do right now? I want you to look back at that probability scorecard and pick one topic, just one, that you feel the weakest on. Spend 30 minutes right now just reviewing that. I promise you it could make all the difference tomorrow. Good luck, you've put in the work, and you've got this. If this was helpful, please hit that like button and go smash that exam.